For this video, we move towards the more interesting ideas of quantitative research, i.e. towards inferential statistics. We start by considering populations and samples. If we want to measure a characteristic called a parameter of a population, e.g. the mean height, then we cannot do so directly. We do not have access to the entire population of interest, and so we must instead take our measures of interest from a representative sample carefully drawn from this population. This means inevitably that what we have measured is in fact only an estimate of, say, the population mean. This is also known as a point estimate. We can, hopefully, assume that with a sufficiently large sample size, and one that has been chosen without bias, that our best estimate of the mean will be a good one, i.e. gives us a value very close to the true value. So in addition to the challenges we discussed in previous videos about the variation that is naturally a feature of a variable across, say, a group of people, we now have the added variability that choosing samples can introduce. You see, we would not be surprised if we had chosen a different sample and then measured a different value for our estimate of the variable height, weight, or whatever we are interested in. However, we might expect this sampling variability to be small if we have large sample sizes, but we must be mindful of its presence. Remember how the variation, i.e. the spread of measures taken within a single group, could be expressed as the standard deviation. Well, now this extra variability, which will be present in all quantitative research, is expressed by something called the standard error, and it is from this that we derive something called confidence intervals. But more about these later. In the last video, I explored core ideas behind descriptive statistics, i.e. measures of the average and measures of the spread of a single group. For the majority of quantitative research, we are concerned with differences, e.g. before and after, looking at the same group, or group A versus group B, for example in a randomized control trial. To explore these measured differences, we use the concept of significance. Significance is expressed in two distinct ways: statistical significance and clinical significance. Now, statistical significance means, could my results be explained merely by chance alone, i.e. are the differences I see across my groups real or just a fluke? Whereas clinical significance asks the question, are my results important? And it is the combination of these two expressions of significance that allows us to draw conclusions from our research. Let's start with the second of these concepts, i.e. is the change seen important? Well, it's really down to a question of judgment, but context is very important here also. Consider the following scenario. Given the values measured as seen here of some experiment, would your gut instinct think the differences measured between these two groups important or not? Most would think it unlikely that we could declare any major conclusions as the values are so similar. However, these were the results from the 2016 UK referendum, namely, should the UK remain a member of the European Union? I think we can all agree that the results in this case were indeed clinically significant. They were indeed important. Here's another example from the following year. The Catalan referendum for independence in Spain on the 1st of October 2017. 90% of those who voted for independence. Just over 2.25 million Catalans voted, and this represented a 42% turnout. So do you think these results are clinically significant? Well, even though 2.25 million Catalans voted, this still represented less than a 50% turnout. And whilst that doesn't negate the answer, the fact that this election was considered illegal beforehand via the Spanish government in Madrid, the suspicion is strong that this result did not fairly represent the population of the entire Catalan region, One might argue that pro-Remainers would have stayed away from an illegal vote for fear of arrest, etc. In conclusion, clinical significance is, to a large extent, a professional judgment that is guided by the numbers and context, but is tempered by expert knowledge. We now move on to the second, but more fundamental concept around significance, namely statistical significance, i.e., is the change seen, e.g. before and after, real, or could any differences seen be due merely to the play of chance? Imagine I run an experiment. I want to know if this difference is genuine or a fluke. So in my experiment, I imagine giving my class two maths tests, once before and once after a series of fun statistics lectures. Here are the results. My class average at baseline was 45%, and my class average after 6 hours of non-stop joy was 51%. So my question is, could this difference, 45% rising to 51%, have arisen by chance? To answer this question, we might set up hypotheses. The null hypothesis states that there is no difference between the groups beyond that due to chance alone, whilst the alternate hypothesis, sometimes called the experimental hypothesis, states that there is a real difference between the groups. To resolve which hypothesis we accept, we either produce a p-value or we look at confidence intervals of differences. Let's take these one at a time. P-values, which until quite recently were the more commonly used method of deciding statistical significance, are simply a probability. A p-value is, simplistically, the probability that the result we obtained was by chance alone, in which case we must be cautious about drawing any grand conclusions about wonderful effectiveness of our intervention. In the last video, I stated it was very useful in considering descriptive statistics to consider the distribution, i.e. the shape, of the variables. And this concept lies at the very heart of inferential statistics. We can have a distribution of the value of a variable, for example here pupil's height, or we can also consider the variables to give the distribution of probabilities of the outcome of various values of that variable. This is different from the idea of a fixed probability, e.g. that of getting a heads with a fair coin. Here we might consider a continuous variable, so it is only meaningful to speak of the probabilities for a range of values, or for values above or below a preset limit. A common distribution seen in healthcare and beyond is the normal distribution, which is also known as the Gaussian distribution. Through studies of its properties, we can make certain statements about the expected proportions of data which should lie between various intervals. And these intervals all correspond to multiples of the standard deviation. So for example, we can say that 68% of our data of a variable should lie between one standard deviation either side of the mean. 95% of our data should lie between two standard deviations of our mean, and almost the entire data set, 99.7% of our data, should lie between three standard deviations either side of the mean. The key one of interest to us here is the fact that 95% of all data lies between plus or minus two standard deviations either side of the mean. What does this mean in practice? Imagine we know the mean height for all 8-year-old boys in the UK is 108 centimetres with a standard deviation of 8 centimetres. This means that 95% of all 8-year-old boys will have heights between 92 and 124 centimetres. This is because if we add two standard deviations, two lots of 8 centimetres, which is 16 centimetres, to 108, we get 124 centimetres. And if we remove 16 centimetres from that 108, we get 92 centimetres, and that's how we calculate those limits that must contain our 95% of all 8-year-old boys. To put it another way, this means that only 5% of all 8-year-old boys will have heights lying outside of the range of 92 and 124 centimetres. In other words, they are either taller than 124 centimetres or shorter than 92 centimetres. And it is this idea that gives us the concept of a rejection region when thinking about accepting or rejecting the null hypothesis. Now, a common convention in statistical significance, so by no means the only convention, is that if the p-value calculated is less than 0.05, i.e. less than 5%, then the data measured was considered good enough to assume that the results we have seen for the differences were not a fluke, and this is because our results would then lie in the rejection region. Here's a quick exercise. Decide for each of these measures if they can be considered statistically significant or not using the p less than 0.05 convention. So here's our 4 results. Without the p-values, we would imagine that the first result, 23.45 versus 45.47, and the last group, 14.8 versus 9.2, would be the most important. However, it is these first and last groups that do not have p-values less than 0.05, and therefore it is these first and last groups that are not statistically significant. The only 2 statistically significant results are the middle 2 results. You see, you have to ensure that you have determined statistical significance before you can move on to the more interesting question of the importance, the clinical significance of your results. In summary, for p-values as measures of statistically significant, if the p-value calculated is less than 0.05, then we can declare statistical significance. If our p-value is greater than or equal to 0.05, then our results cannot be declared statistically significant. And as a final thought, it must be emphasized that in research you have to determine statistical significance before you can make any claims about clinical significance. I have seen too much research where the p-values have either not been given or have been greater than 0.05, and then the authors still talk about the importance of their results. This is a classic example of pulling the wool over our eyes. Okay, let us now move on to confidence intervals. Now, confidence intervals are not only used as measures of statistical significance. In fact, they are mainly used as measures related to the precision, say for a single measurement. However, they can be used sometimes as a way of determining statistical significance, and we need to separate out these 2 uses of confidence intervals. This idea of precision is when confidence intervals are used for a single measure, and the idea of utilizing them for statistical significance is when confidence intervals are calculated for the measurement of a difference, say across 2 groups. At heart, confidence intervals represent an estimation of a population parameter calculated using the sample mean, the sample spread, and the sample size. It does this by starting with the mean, the point estimate, and calculating a range of values above and below the mean to give what is often called a plausible interval in which the true population is likely to lie. Now, in many research papers, we meet confidence intervals expressed like this. So here we have the mean of some measure equals 23. Now the 23 is the measured value from the sample. And then the calculated confidence interval, the 95% confidence interval in this case, has the interval with lower value 21 and upper value 25. And it is this interval of between 21 and 25 that we claim is a plausible range that can be seen as a kind of precision for our sample mean as an estimate of the population mean. The closer together, i.e. the narrower the interval, then the better the precision, and this is achieved, not surprisingly, by increasing the sample size. I find it helpful to visualize the confidence interval using a number line. So using the same measure of mean with its attendant confidence interval, we can express this visually. So there we can see our measure of 23, the yellow dot in the middle, and the plausible range, the 95% confidence interval, is expressed with the horizontal bar going from 21 to 25. Now the link between confidence intervals and statistical significance occurs when we measure a single confidence interval to look not at one measure but at the difference of two measures. Imagine I have run two experiments with different sample sizes, and it just so happens we've arrived at the same value for the means in both cases. Nevertheless, we will calculate different confidence intervals for these two experiments, as the confidence interval, as already stated, shrinks as the sample size increases. So here are the two measures visually. For experiment 1, I had 23 in the first group with a confidence interval of 22 to 24, and 26 in the second group with the confidence interval 25 to 27. And here it is visually. Then for the second experiment, the same two values of means were measured, 23 and 26. But now you can see that the confidence interval is wider. So what do we notice? Well, in addition to the confidence intervals being narrower on the left-hand side compared to the right-hand side, i.e. better precision, remember, crucially, it is the fact that there is no overlap on the diagrams on the left, but there is overlap on the diagrams on the right. Where overlap occurs, we cannot state that we have statistical significance. If overlap does not occur, then we can say we do have statistical significance, and it's to do with that null hypothesis. Let me explain further. For experiment 1, when we compared 23 and 26 with the narrower confidence intervals, if we work out the difference, which we can clearly see is 3, but the confidence intervals, we obtain the upper value by taking the 27 from the 22, the smallest value from the largest value, whereas the lower value of the interval, calculating 25, take away 24, which is just 1. Visually, you can see our difference is 3, and it runs between 1 and 5. Now remember the null hypothesis. The null hypothesis says there was no difference between the two groups. Now here, the entire range of plausible values runs between 1 and 5 and is centered at 3, but nowhere on that range is the value of 0, no difference, a possibility. Therefore, we can claim statistical significance. Compare and contrast this with experiment 2. Here are two values with the same measures of mean but wider confidence intervals, and when we work out our difference, the difference of course is 3 still, but our confidence interval is much wider. Our upper value is 28 take away 21, which is 7, and our lower value is 24 take away 25, which is minus 1. If we look at this visually, we can now not only see that our confidence interval was wider, but more crucially, in the range of plausible values, 0 is a possible contender. Therefore, we cannot reject the null hypothesis, and therefore we cannot declare statistical significance. Now that's quite a bit to get your head around. You might need to review this section more than once. So what I'm saying is that confidence intervals are linked to statistical significance only when we use a single confidence interval to look at the measure of differences. In summary, if confidence intervals are used on a single measure, then they can be interpreted as a measure of precision. The higher the sample size will give a greater level of precision in the evaluation of the mean. If confidence intervals, on the other hand, are used with differences between two measures, then if that interval of plausible values contains 0, then the results are not statistically significant, and vice versa. And that's the end of part 3. Thanks ever so much for listening, and well done for getting through to the end.